All right, so it's still before the first talk, but it's my pleasure to welcome all of you at the Post-Snowden Cryptography Conference here in Brussels. So the reason that we can have this conference, of course, you all... Of course, I know you all pay your registration fee, which covers your drinks and food, but the reason that we can actually have such a nice lineup of speakers is that we have an EU project called Qubes CSA, which is covering the speakers that is part of the registration. Something is not really reporting. Is it magnifying? It is. All right, so today and tomorrow we have a nice program. 4 speakers today, 6 speakers tomorrow, if you look at the schedule, which you have most likely seen at the entrance. Then today we have 2 talks, then a coffee break, and then after the last 2 talks, there's a 1 hour to get to the restaurant. So La Manufacture is we're going to have the conference dinner. There will be some drinks to welcome you, so starting 7:30. Afterwards, it's a seated dinner. If you have any dietary restrictions or wishes or whatever that you notified us with the registration, you should receive some snippets from us so that you can alert the restaurant people that you're one of the special people and that you don't get the general food. And then tomorrow we start again in the morning, 9:30. Tomorrow, the end of this event is the coffee break. And as you can see, the coffee machines are there, so we don't have just half-hour coffee break. We actually have all the time till they kick us out of the room, which should be like 6 p.m. So that means please plan on having some time here, interact with each other, interact with the speakers. The reason that we're all here together is, of course, to listen to some fantastic talks, but also to solve the problems of the world and get more security. And that is not only done by listening, but it's also done by talking, by interacting. That's why we decided to end with a coffee break. Those who are just here for seeing the pretty faces can go then, and those who actually are here for making a difference can stick around, can talk, and, well, something like 6 or 6:30, I fear that the hotel will want their room back. All right, so I've said enough. It's now my pleasure to introduce the first speaker, Joanna Rutkowska, who is going to talk about the Qubes project. So it's talk about Qubes OS, about towards secure and trustworthy personal computing.
Okay, so I have only 45 minutes, but I thought I would have 1 hour, so I'm going to be quick, really. So Qubes OS, can we maybe dim the lights a little bit more? Because I have dark slides, so it's a reasonably secure operating system for personal computers. It implements security by compartmentalization. It's not a hypervisor, which is what people often confuse it with. It's just a user of a hypervisor. Currently, we use Zen. It's also not a Linux distribution because it packages, it might be using lots of templates representing different distributions. If anything, it's a Zen distribution. Are there any Qubes users here? Can you? Okay, that's nice. So why, sorry. Why do we need another operating system, secure operating system? It's because, first, I think we really need secure personal computers. And this is because the personal computers are really our eyes, ears, and fingers, which means they can always see and hear and all the secrets that we have, whatever sophisticated crypto algorithm we use, or whether we trust the infrastructure or not, at the end of the day, all the confidential information or our life secrets all end up on our endpoint devices, on our personal computers. So if they are compromised, then everything is lost. So they are really extensions of our brains, especially if you look at people, how they treat their phones, their smartphones. They put like whole their life into their smartphones. And as I said, nothing works when client systems are compromised. Can you actually see the slides, the text there? Yeah? Okay. So present mainstream personal operating systems are really insecure. There's not much to disagree about this. Just to give some examples, we have attacks, or to say it differently, the personal computers are plagued by all the attacks coming through legitimate but buggy applications such as web browser, PDF readers that might just get exploited when parsing an untrusted input, or it might be a malicious application that the user just wanted to install, perhaps some stupid game. Attacks coming through malicious or just infected USB devices, like lots of them we connect. We want to connect to our personal computers every day. Attacks coming through networking stacks. Probably most of you, when you travel, you connect to a hotspot at the airport or in a hotel, in which case you are risking that your Wi-Fi driver or DHCP client gets exploited if it has some bug. And of course, it's only reasonable to assume that it does have some bugs. Also, maybe less well-known problems with attacks coming through malformed file system or volume metadata, such as a malformed partition table or malformed ext4 or FAT metadata. So you don't really need USB with all its bloated USB stacks. You can just be inserting something, you can be parsing an image or even a CD image perhaps that triggers a lot of parsing in the kernel and exploits your hypothetical bug in partition parsing, partition handling code in kernel, again compromising your whole operating system. There's also widespread problem with lack of GUI isolation, meaning that every application on my personal computer can, I especially use personal computer rather than Linux, Windows, or whatever, because they all behave the same. So whatever application on personal computer, whatever graphical application is able to sniff this take a screenshot of the other applications, which is obviously silly. Or especially recently, malware which somehow got and compromised the personal computer, later infecting the firmware on this computer, such as the BIOS, and persisting itself across a further reinstallation of whatever operating system we will bring later. So I believe that most of these problems, all of these problems, are actually because we use monolithic systems which have monolithic architecture, which means that there are way too many components that share the same, that are part of what we call trusted computing base. There really should be no reason why our most trusted part of the system should host Wi-Fi drivers and Ethernet drivers and TCP/IP stacks and USB stacks and all the various file system modules, so file system parsing code, and exposing all sorts of exotic APIs to any application that asks for it. There should really be all these services, all these components should not really be part of the TCB. So I'm using the term TCB. Can you raise your hand who understands what TCB is? Okay, so TCB is just a trusted computing base, something we want to minimize. We don't want operating systems to have big TCBs because this is good. Again, I'm going to spare this slide for this audience. This was explaining the difference between trusted, secure, and trustworthy. So it's important to realize that monolithicism is not just about the kernel. It's about the whole design of the whole operating system. Because from the user point of view, it doesn't really matter whether the attacker gets ring 0 or ring -1 or whatever privilege access. For the user, what matters is whether the attacker gets access to the user's precious data. So, for example, having a monolithic GUI server, which might not even run as root, it might be running as a normal user. It still is not a solution to anything, because if it's monolithic, if it's easy for the attacker to get into such a GUI server, which presumably will be implementing some kind of isolation between different applications, which current GUI servers do not, by the way. But assuming it did implement it, it's still, if it's a big monolithic bloated thing, it doesn't matter whether it runs this root or not, it's still bad. Because, of course, the GUI server sees all the user's secrets. Right. Monolithicism extends also to other subsystems like the horrible things like dbus and UDEF scripts or whatever. You probably know all these things. Finally, something that is becoming increasingly important and noticeable is the hardware. Up until recently, it was a no-brainer for us security architects to assume that the hardware is trusted. Right? It's obvious. The whole hardware, all its peripherals, all the devices. If you look at how most operating systems treat them, they all are part of the TCP. And of course, this is very unwise. Not only because it's possible for the attacker to attack some of the hardware. For example, network card might have its own little computer, and there have been some attacks on embedded computers in networking cards several years ago. But also because all this hardware, networking devices, disks perhaps, Wi-Fi devices, all might be backdoored by the vendors. So we should somehow deal with that. Right. So as you figured, I don't like monolithic much. So how to solve the problem? We have two approaches, as I see it. One is to ensure that whatever TCB, again, not just kernel, TCB everything, TCB all the hardware, all the devices on this laptop, the GUI server, everything is good. I intentionally said good, not secure. Because, again, something that is secure might be not necessarily good to the user, obviously. For example, Intel Management Engine is probably very secure, but it's something that I would not call good. So if we take this approach, ensure TCP is good, or trustworthy, perhaps I should have said, it means secure. If we want to ensure that, if you want to say good is secure, because obviously something that we want to be good must be secure. It's a condition, of course. So secure, so difficult to attack. So we have some technologies here, some approaches like all the various anti-exploitation technologies like ASL, address space randomization, non-executable various things like DEP and SMAP, etc. And there are projects such as GeoSecurity, as well as even the mainstream operating systems in the recent years, adopting these technologies with quite a reasonable success, but this is only up to a certain point. It's just trying to rescue this whole big bloated creation by making the exploitation harder. And as we are witnessing this over and over again, this still does not solve any problem. Because seriously, I remember first articles about stack guard, so protecting the return address on the stack back in, probably that was either late 90s or early 2000s. And every time somebody discusses such an anti-exploitation technology, you can feel how the author believes that this is now like the elimination of this class of attacks. So somehow this still did not solve anything. Also remember, exploitation is just one part of the threat. Another part of the threat, as I mentioned, might be intentionally backdoored programs, firmware, or hardware. And of course, this will it usually will not solve that backdoored, untrusted component problem. Right, and that's the other branch I have here. So ensure something is good means something is not backdoored. And that we can ensure using code review or requiring that something will be open source or somehow transparent, verifiable. Specifically, Intel Management Engine is a great example of a failure in this respect. So the other approach, again, the industry have been trying to implement this left branch for at least a decade, and it somehow still doesn't work because still our operating system, our personal computing devices are still really untrustworthy. So the other approach is to get rid of the TCB, or at least to minimize it as much as possible. So this is nice because once we get rid of the TCB, we just don't need to care whether this code is buggy or so secure or not, malicious or not. And that's exactly the approach that we have taken with Qubes OS. Right, I also added that code review open sourcing also helps to make things more difficult to attack. So security by isolation is the principle, the paradigm that Qubes OS use. That's a picture that you probably already know. So yes, we use virtualization for isolation. Specifically, we use Zen, but that's not important. But the question that you might be asking yourself, or many people ask, is why would VMs provide any better isolation than the regular process isolation as is provided by any other mainstream operating system, such as Linux? Is there anything wrong with a good old x86 MMU? Have you ever heard about any exploiting the MMU protection on x86? Have you? Interesting. Is it public?
I have seen it in Hamburg.
How, do you remember the name? Interesting, because I've never heard of it.
It was about running Turing complete code on MMU.
Okay. It was on the Intel x86? Do you, okay. The question was, I said, I was hoping to ask a rhetoric question. Have you ever seen an exploit against MMU protection for Intel x86 processors? And the gentleman here said, yes, I saw it at Hamburg at CCC 3 years ago. A few years ago, okay. Which was a surprise to me. Anybody else heard about breakout from MMU? Jake. I don't believe microcode updates can reflash anything because microcode updates by itself is not persistent. Microcode updates only is it's not persistent. It must be applied every time by the BIOS. Okay. Sure. But if you control the BIOS, you don't need exploits to break out of the privileged process, right? So I don't know what you heard about, but the gentleman here, but I never heard of such an exploit.
There was the Blockhat this summer attack that gives you from ring 0 you can get ring -2 using.
Okay, that was from ring 0 up. This is not the good old MMU story, right? Because from ring 0 to SMM and from ring 0 to ME, this is a different kind of story because you are already at the kernel level, at ring 0. So it doesn't count. My question was, what's wrong with the good old MMU? From user mode to kernel, from ring 3 to ring 0. So I never heard, and for the last 3 decades, I have never seen an exploit for escaping from MMU sandbox user mode process to kernel mode. And I believe there was no public presentation on that. Otherwise, I would probably have heard about it. So back to this presentation. So what's wrong with this good old that we need to use virtualization? Because this is maybe just adding an additional layer of complexity. So there is something special about virtualization, and this is 2 things. First, it allows to reduce the interfaces. This is actually one thing. It allows to reduce the interfaces exposed to untrusted applications that we want to sandbox, while at the same time allow us to run the legacy applications. Okay? Because otherwise, if we were to design our own operating system with our own new APIs, with our own new drivers and own new subsystems and own new applications, like, for example, Norman and friends have been doing, we don't really need a virtualization for that. We still might use it, but we don't really need it. We can use MMU. But for Qubes, our goal was to be able to run all the existing applications and drivers, and most of the drivers. For example, I'm running this presentation out I'm using Microsoft PowerPoint here, just because I can. Just because it looks nice, right? I would not be able to do that without virtualization, of course. And this is, of course, all Qubes, right? So, but before we get too excited about virtualization, we should realize that the VM hypervisor interface is not the only critical part. There's a lot of attention now in the industry to advertise solutions such as we use micro-virtualization, whatever, nano-virtualization, pico-virtualization, right? So they stress the simplicity of the hypervisor. Indirectly also simplicity of the application to VMM, to hypervisor interfaces, which is supposed to convince us that this is a super secure solution. But as part of the storage, only part of the storage, if we have 2 isolated compartments, enforced by some very strong, perhaps formally verified microvisor, whatever. The problem is that if these 2 VMs want to cooperate somehow, perhaps they want to exchange a file. So if one of those, if the receiving end of this green one here is complex, unsecure code, then the one on the left can just send some malformed input and exploit a hypothetical bug in this green one and compromise it. And this happens irrespective of what kind of hypervisor we have, whether it's formally verified or not. This is an orthogonal aspect that we should remember about. So the strong isolation turns out not to be so strong anymore. Right, so the lesson from this so far is don't get too excited about hardware virtualization. because virtualization is nothing magic. The only useful part of it is that it allows us to have the legacy applications and reduce the interfaces the TCP exposes to these legacy applications. Except for maybe two technologies that are actually useful that have not been here before virtualization. And these two technologies, especially the first one, is the IMMU. The IMMU, or on Intel platforms called VTD, is something that is necessary to the privileged drivers. Before IMMU, we could not have meaningful microkernels with the privileged drivers. So that's one of the unique benefit of the virtualization. And also, especially recently, I have become convinced that second level address translation like EPT brings benefits. Because if we compare the complexity of the code handling, let's say Zen PV VMs and Zen HVMs with SLAD, the latter would be much less complex, and things such as XSA 148 should not happen that easily in there. XSA 148 was a terrible bug in Zen disclosed this year. Right, here are the slides I just told you about. The IMMU is one of the beneficial technologies. And it's important to mention here that Qubes OS has been making use of these technologies since the very beginning. We have something that we call net VMs, where you assign your networking hardware, such as Ethernet, Wi-Fi, and then all the code, all the drivers, all the OS/2.11 stack, all the TCP/IP stack, all the DHCP client, all runs in a VM that is just a VM. And if it gets compromised, well, you can just restart it. That's pretty nice. We also have support for VMs that host USB devices. And the recent 3.1 RC1 that we released yesterday offers by default an option to assign all your USB devices to a VM also. That is to solve the problem of plugging in various different untrusted USB devices, and not fear that this USB stick that I'm going to plug in to copy my slides is going to compromise my personal computer. I think I'm going to say more about it in a moment, just to signalize. Especially nice is it's especially nice that we can have encrypted USB, and we can plug into a USB VM. You have the USB VM handle all the USB processing in the kernel, and then we can terminate the encryption. We can run the looks, the crypt setup. We can run in another VM, which is not involved with the USB parsing and processing, which is pretty nice because we can decompose this process into something that is untrusted but is complex, the USB handling, and something that operates on the sensitive data, which is the actual decrypting of the volume that is there. As a bonus, with these VMs, we also get some resistance to malicious hardware. Originally, when we were designing Qubes, we had in mind mostly resistance to attacks, like sitting in an airport, connecting to a Wi-Fi, my Wi-Fi driver being exploited by somebody sitting next to me. But the same technology, the same approach, allows us not to care much about NICs or USB devices to be intentionally malicious, which is quite an achievement, I think. Theoretically, we could also We could also deal with, with a malicious disk and SATA controller. Although SATA controller doesn't make much sense. It doesn't make much sense to consider SATA controller as not part of your TCB because it's on recent processors. It's part of the processor itself, which we need to trust anyway. But the disk, it's debatable whether the disk itself might be harmful, and apparently the SATA protocol allows for the disk hardware to request some DMA transactions, which the SATA controller, the driver there might just approve, even though we might be using something like Qubes OS. So theoretically, we might use IMMU to put also disk hardware outside of TCB, although we don't do that. And we don't do that because it requires a very solid trusted boot scheme, which we unfortunately still don't have on x86. We could also theoretically deal with malicious GPU device, but then again, this in practice doesn't make much sense because GPUs on most laptops are part of the processor package itself, so which we need to trust anyway. A slightly different story is with a malicious BIOS, SMM. Of course, Qubes makes it hard for the malware that attacked one of your VMs, such as a web browser running in one of your VMs, to infect the BIOS, because the attacker would have to escape from the VM, get to dump 0, and even from dump 0 might not have enough powers to reflash the BIOS. But we cannot do much if the BIOS got infected or is malicious before we install Qubes on this laptop. In theory, for some years I believed that Intel TXT would be a solution to that. In practice, it is not a solution. It's not only we have shown several spectacular attacks against TXT, it's also questionable whether TXT could be considered a trustworthy technology at all. And even more problematic is Intel Management Engine technology. Again, for some years, I used to believe that we could deal with Intel ME using IMMU. Unfortunately, I was misled, and the recent book published wrote by one of the ME architects from Intel makes it clear that ME bypasses any IMMU protections. So we don't have protection from Intel ME, sadly. So we've been talking so far about isolation, but there's another aspect that people often forget about when they get excited about Qubes. Is that Qubes is not as much about isolating as it is about integrating of the typical desktop workflows. Because the isolation itself does not really solve much problems, at least not on the personal computing in the personal computing field. So let's say you have 3 VMs, say 3 Windows VMs. What makes you think that, and one of this might be personal, the other work, the other banking, right? What makes you think that your personal and work will not get compromised after a few weeks, each on itself? Because maybe in each of these VMs you would be opening PDFs, or you will be browsing web, or you will be doing whatever thing that you normally do, all this normal activity that we know, the normal operating systems, like those that are running inside those VMs, usually that they are not prepared to handle. So what makes us believe that after a few weeks, it's not that all of the VMs will get compromised. In fact, that's what will likely happen. That's why when I see yet another vendor announcing they have just came out with a super security solution that offers, say, dual personality system for your phones. You have work and personal. This is really meaningless. Again, each of these VMs will get compromised because these are just normal VMs, normal operating systems. Normal operating systems not prepared to handle typical desktop flows. So here is how to use integration somehow smartly to solve these problems. Here's an example with opening PDF. Rather than open it in my usual personal or work or whatever VM, I delegate it to be opened in disposable VM. This is what we call VMs that are just created ad hoc and then destroyed after we finish working with a document. Here are other examples of smart integration that we do on Qubes, such as Split GPG, which is things similar to Smart Card, only that we have this between VMs for storing the GPG keys. Qube Store and VPN VMs, especially the Unix. We have recently, not so recently, integrated Unix with Qubes, where you have a different VM for actually running the applications, like the Tor browser, and a different one for running the actual Tor process, and yet another VM for running the networking stacks. So again, this is all integrated workflow decomposed to different VMs. Or Qubes File Copy, where we have a special protocol for copying files, which does not require the receiving VM to do any kind of parsing of complex metadata, such as partition table or file system metadata. Or using the encrypted USB sticks that I mentioned a while ago. When you plug in a USB stick, it is encrypted. The USB processing is handled in one VM, but the encryption is terminated in another one. So it's important to realize that Qubes is not just security by isolation. It is really a clever integration of these isolated components. Clever meaning not hopefully weakening the isolation. That's why I thought it's might be better to call it security by compartmentalization, to stress this isolation aspect, also integration aspect. And let me just reiterate that we focus on personal computing because all these problems we just been discussing are really typical for personal computers and not for servers. And finally, let me just quickly get back to this problem of security versus trustworthiness. So there are also some problems with trustworthiness that I mentioned, such as the malicious BIOS, malicious disk, malicious Intel management engine that we currently cannot deal with using software-only approach. There are also other problems such as development security and build security. Especially the build security is a problem. So if somebody builds Qubes OS, such as Marek builds a new release and puts it on a server, how do we know that his computer that he used for building it is not infected and the the rootkit there will not inject some rootkits. That's why a lot of work in reproducible builds is really of crucial importance here. What reproducible builds can offer is that they can allow multiple people to build the same binary, compare it bit by bit, and then to sign the same binary with their own keys. So we can get a Qubes ISO or Qubes updates that will have not just one signature by Marek or myself, but they will have n signature and signatures of some n number of people, which is very desirable. And dealing with backdoored hardware or malicious hardware is a big topic, and this is the area of increasing importance. And it's a topic for another presentation. So just quickly, the status. 2010, we actually started working on it at the end of 2009, but 2010 was the first release. Release 2, release 3 was last year, and just recently we have released 3.1 release candidate 1 just yesterday. It brings the management and pre-configuration infrastructure, which is important for preparing customized, pre-configured configurations of cubes, such as we will be able to do out-of-the-box Unix setup, or maybe out-of-the-box Thunderbird plus GPG plus GPG setup, or whatever you want. And the point is that the management stack, which is based on Salt, it offers ability to prepare configurations in a declarative manner, which allows for very complex configurations to be easily prepared. And finally, just an obvious thing that Qubes OS is just a platform for running secure, privacy-focused applications such as Tor and secure email and whatever other you want. I think that's pretty obvious. Here's the Qubes master key in case you wanted to verify it. If somebody wants, I can read it out loud. Okay, so I think we have some 5 minutes for questions. So.
Please line up at the microphone. For questions, please line up here. Thank you very much for the talk. And it would be great if you could state who you are.
Hi, I'm Nicolas Courtois. I have two small questions. So what is the budget of this project, and how much of code which you have not written and you have no control on that you use inside this project?
Let me address the second part, which is the most interesting. We have a lot of code that we have not written. This includes all the Zen hypervisor, which is a critical code. And if you look at the Qubes security bulletins, we maintain a page where we display and describe each security problem with Qubes. We are at 20-something right now, after 5 years. Majority of these, I would say 80%, relate to bugs in Zen, sadly, which we have no influence to. I have my own issues with Zen. I don't believe that Zen is the most security-focused product, and the attitude is more towards features than security. On the other hand, if we look at the mainstream hypervisors, the actual practical hypervisors that work, that support S3 sleep and support running modern graphics drivers in something like DOM0, something we have in DOM0, then, and at the same time having a proper architecture allowing us to do NetVMs, USB VMs, then Zen is currently the only candidate still. unlike KVM, for example. Okay. And of course, there's also lots of other code. For example, in DOM0, the whole Linux kernel in DOM0, we just accept as it is. We just verify the signature. So the verifying of the signature means is important that in case there was a backdoor there, we can see who introduced the backdoor. That it wasn't Qubes team, that it was somebody at the kernel org, right? But DOM0, because we have taken lots of steps to make sure that all the code that runs in DOM0, so that the privilege partition is essentially practically not reachable for the applications from the outside, from the VMs. So it shouldn't matter much that, another thing, we use the whole Xorg server, we use the KDE environment. There are also other environments supported. But the point is, even if there is a bug in KDE, which there are probably millions of them, they are not really reachable by the untrusted applications because, for example, there is no networking to DOM0 and there is no other channels. Okay, Jake.
Just one question. Thanks for putting up the fingerprint of the project. That's really important for establishing a root of trust. But have you thought about adding like GRSec specifically to the DOM0 kernel so that it's significantly, I mean, the Linux kernel is a steaming pile of features. So okay. I wonder if we might make it harder to exploit those features, and what are the practical ramifications of all of the guest kernels also having GR security and taking the subgraph approach of compartmentalization. So it's basically, Yodag, I heard you like compartments, so I wanted to put a compartment in your compartment so you could compartmentalize all your compartmenting. I wonder if you could reflect on that a little bit.
Okay. So first, I believe that if we wanted to introduce GRSec, the VM kernels should be first before DOM0, because DOM0 kernel, again, we don't care that much. We don't really care if it might have exploitable bugs or not. However, the VMs might make sense. Currently, it wouldn't make sense, because currently we don't have any kind of user versus root isolation in VMs, just because we don't believe there's any meaningful one. I have spoken a lot with the subgraph project people, who have developed or are developing subgraph OS, which also implements a compartmentalized approach. However, it doesn't use virtualization. It uses a lightweight approach based on the Linux containers, Linux namespaces isolation, as well as seccomp filters, and GRSec hardening of the kernel. And it's, in my opinion, it's a no-brainer to integrate subgraph with Qubes, subgraph running in Qubes VMs. So to have a subgraph OS template for Qubes OS, that would be just great. Also because it would allow for more lightweight and finer grade compartmentalization of some of the VMs. For example, I might just have one work VM, not 5 work-related VMs, or 15, as I have probably. I'm not sure if I have not missed any parts of your questions.
Thank you very much for the questions. I'm cutting off John Solwers because he can give his own talk later on.
Okay.
So he can at least give the answers if he doesn't want to give the questions.
Okay.
So please join me in thanking Joanna again.
Okay.